Free-floating, waste-gated, and VNT turbo all include a CHRA, or Center Housing and Rotating Assembly. This includes the high-speed rotating parts, often called the rotor assembly, and the components used to control those parts. It may contain as few as 8 or as many as 25 separate components, all produced to extremely tight dimensional tolerances and made from the highest grade materials with specialized surface finishes, each specifically chosen for the task and operating conditions. The shaft wheel assembly is made from 2 pieces, a high-grade steel shaft and a turbine wheel head, which may be made from any of 3 different superalloy materials to suit the operating conditions of the turbine. The turbine wheel head is welded to the shaft, which for modern turbos is completed by electron beam welding. The welds are extremely strong and reliable. The finished shaft wheel assembly must then be balanced to ensure reliable, quiet operation at very high speeds. We balance the turbine wheel dynamically in 2 planes, and you will see that metal has been removed from the back face and from the nose of the wheel to comply with our stringent balance specifications. Each cast or machined feature on the shaft wheel assembly is designed for a specific task. On the turbine wheel, exhaust gas enters through the inducer section of the blades. The blades are a complex aerodynamic shape designed to maximize the transfer of energy from the exhaust gas and convert it into wheel rotation. The contour section follows precisely the shape of the turbine housing contour, with very small clearances to maximize efficiency. And finally, the exducer is where the exhaust gas passes out of the turbine to the exhaust system. The piston ring groove or grooves are part of the turbo sealing system, and in conjunction with the piston rings forms a highly effective sealing system to maintain the oil within the center housing and prevent leakage. The detailed operation of this system will be seen in a later training course. At the end of the hub section is an oil thrower, which will be explained later. The shaft bearing journals support the fully assembled rotating components in conjunction with the journal bearings themselves. The center of mass of all the rotating parts is located at the turbine end bearing journal, and this is a useful feature to remember when we study turbo damage analysis in later training courses. The pilot shaft and the very accurately machined shoulder are where the thrust collar, thrust spacer, and compressor wheel are located. The thread at the end of the shaft allows a lock nut to be fitted, applying tension to the shaft as the undercut area below the thread stretches slightly, compressing all the components together to ensure that they cannot loosen during operation. To achieve this, the nut is tightened in stages. First, seating torque is applied to compress the parts into their correct position. Then the nut is loosened, followed by tightening to a specified torque, and finally applying an accurate angle of twist, which ensures the correct amount of stretch to the shaft. The tightening process ensures that the lock nut cannot loosen during normal service. Our turbochargers are assembled from precision-engineered components. For example, if we look at one of the bearing journals on the shaft, for good control of the rotating assembly and reliable, quiet operation, the journals need to be as close as possible to a perfect cylinder. We work in microns, which is 1/1000th of a millimeter. A typical tolerance on that cylindrical shape is just 2.5 microns. To understand these small sizes, we can compare to a human hair, a human blood cell, a particle of dust, and a tobacco smoke particle. We store and assemble these parts in very clean conditions. The new turbocharger must also be installed onto the engine with care, using only fresh, clean oil of the correct type. Oil from the engine lubrication system enters the turbo and is distributed to the journal and thrust bearings. All turbochargers use two oil films, one between the center housing and journal bearing, and one between the bearing and the shaft. The clearances are often mistaken as being excessive play when examining a new dry turbocharger. But this is correct and necessary for the correct functioning of the turbo. The oil flows through both the journal and thrust bearings. Oil throwers at the turbine end and compressor end then collect the oil and return it to the engine sump. Notice that the oil inlet is much smaller than the oil drain. Full details of the bearing and oil system will be explained in a later training course. The oil also has another important function: to cool the rotating parts and bearing system, preventing damage due to heat soak from the extremely hot turbine end. When the engine and turbo stop, the cooling oil flow stops and the temperature in the bearing area reaches its maximum approximately 2 or 3 minutes later. If the temperature is excessive, this can cause the residual oil in the bearing to burn and turn to hard black carbon, called coking, which will rapidly damage the turbo. The use of a shroud or heat shield controls heat soak by diverting the path of the high temperature away from the bearing system towards the turbine housing flange, reducing maximum temperature in the bearing area. This simple part is highly effective. But for higher temperature conditions or where cooling airflow is minimal, we may use water cooling, connected to the engine's own cooling system. Even when the engine stops running, the thermosiphon effect of the system continues to cool the turbo. Compressor wheels have complex aerodynamic designs optimizing pressure, flow, and efficiency for each application. Ambient air enters via the inducer and exits at high speed from the exducer section of the blade. Air passages formed between the large main blades are often divided by smaller splitter blades to optimize performance for many applications. The wheel is balanced in two planes with balance cuts typically on the nose and back disc. All components are then assembled following a tightly controlled process, which includes many poka-yoke devices to help eliminate possible errors of wrong components or incorrect assembly. A red light prevents operators from passing errors forward to the next stage, and green lights indicate a correctly completed process, which then allows the next stage of assembly to continue. The last stage of the assembly process is to correctly tighten the lock nut, test for oil leakage, and then the CHRA passes into the high-speed VSR machine for a balance check. Any final balance corrections are made at this point, and then the finished CHRA is ready for assembly into a turbocharger.